There's starch and there's cellulose. Which one can you not digest? Break down. Yeah, cellulose. But if you look at their structures, they're nearly identical. The only difference is this bond angle that happens in this repeating unit. So just because of that one bond angle or that slight shape difference, you can digest or break down one and not the other. And this shows you how shape significantly can affect physical properties. And so shape is a big deal. And when we do Lewis structures, we're going to start looking at shape to figure out what the shape is. And as you'll see as you go on in future classes, how that can affect physical properties quite a bit. There's two types of shape that you'll need to know about. There's the, let's see, I want to use the same terms as your textbook. There's the molecular geometry and the electronic geometry. So there's going to be two different types of geometries, electronic and molecular, that we're going to take a look at. Now, you'll have to know something which is probably pretty obvious, but let's say these dots were atoms, okay? This would be the bond length, and we'll have to know something about bond angles, okay? So you will have to remember some bond angles or be able to calculate some bond angles. Okay, and the shape theory we're going to use is an acronym, VSEPR, which we say Vesper, Valence, Shell. Again, this is the theory we use to determine shape. Valence shell, electron pair, repulsion. Basically, the idea is valence shell electrons, or electrons in the valence shell, those are valence electrons, as pairs, okay, repulse each other. Thus, electrons don't like other electrons because they all have negative charges. So, according to that is where we come up with this whole idea of Vesper or shapes. Okay, so let's try this out. I need to move this over, and I need to be up here. Okay, so, it's okay. So, let's say I have an electron in my heart, okay, I'm a chemist, and I have electrons in each of my hands, okay, one right fist and my left. What shape should I undergo to allow the electrons to be as far away as possible from each other? Just linear, okay? So it's called linear. That's the first shape name you need to know. And what would be the bond angle? 180. Yeah, 180 degrees. It's 360 divided by 3, or by 2. So now let's say I have an electron in both hands, and then one in my feet, but I'm going to keep my feet together. I'm not going to move them. What shape do I need to take? Not a T, but a Y type shape would be a little better. What's the bond angle here? 360 divided by 3, or 120. So 120, and this is called Trigonal Planar. Trigonal because it's a triangle, equilateral triangle, and it's planar, it's flat. So Trigonal Planar is the second shape name you need to know. Okay, let's do the next one now. Let's say I have an electron in each hand, and one in each foot, and my feet can be separate. What shape do I want to take down? Star. That wouldn't quite work, because I don't know, it would be a four-sided star, I guess. X, but that's not quite good enough. Yeah, I need a slight twist. Okay? So an X with a twist. Didn't know I could do that, huh? Okay. Does anybody know the bond angle for this? Not 90. It has to be bigger than 90 because I'm here, but it's less than 120. It's great. Good calculation on your part, 109.5. And that shape would be called tetrahedral. This, I'm referring now to page 90. Tetrahedral would look like this. Here's tetrahedral. Okay, see the tetrahedral shape. Okay, so we just did this first section right here. Again, this is page 90. It's also in your textbook. Textbook's a little less interesting to me, but it's on page It does a pretty decent job though on page 374, 375. In the textbook, this is 2 pages. Here I've just made it 1 page. We're going to ignore the last column right now. We're going to come back to that. So ignore the last column for the moment. And based on the electron groups, 2 groups, you already told me it's linear. We'll get back to some of these columns in a minute. Linear is 180 degrees. Trigonal planar would be 120 degrees. Now notice trigonal planar though for a moment. Trigonal planar, if I remove one group, so for example, here's trigonal planar right here, okay? If I remove one group, like this, do you see how it's now called bent? So trigonal planar with one missing group, or a lone pair right here on the top, is now bent. Same bond angle, this is an ideal bond angle, but you can lose groups and have new names. So this column here is the molecular geometry name, and this is the electronic geometry. So if I took the trigonal planar and I replaced this for a lone pair, so I made this, okay? This, the electronic name is still trigonal planar, but the molecular geometry name is now called bent. So it has 2 different names, depending on if we're referring to the electronic geometry or the molecular geometry. If you take a look at tetrahedral, now let's go back to tetrahedral. There's tetrahedral right here. Tetrahedral has 4 groups, so 4 electron groups, and has 109.5 degree bond angles. You can actually calculate that, but it's a little difficult. I'd encourage you just to memorize this number. Now, if a tetrahedral lost one to look like this now, then you can see how it forms kind of a pyramid, a short pyramid, and we call this trigonal pyramidal, meaning a pyramid with a triangle base. So this is trigonal pyramidal, still the same ideal bond angle, and then I can remove a second one to make now 2 lone pairs, still 4 groups, and we call this bent, just like up above, but there's 2 lone pairs instead of 1, and it still has the same bond angle. Okay? I'll come back to this in just a second. Let me show you one more picture. This is, I believe, from your text. You could do, if you're like a carny sort of person and you like to make balloon animals, or you're just strange, if you put 3 balloons together, following the same kind of repulsion thing, a balloon's not going to be like kind of in another balloon. So you have the trigonal planar, the tetrahedral. Once you have 5 balloons or 5 groups, this is going to be called the Trigonal Bipyramidal. I'll show you why in a minute. And then 6 groups is going to be an octahedral. And I'll show you where they get those names in just a moment. But you'll have to know these names. Now let's focus, we did the tetrahedral, let's do the trigonal planar now. Again, you don't need to know the last column. If there are 5 groups, I would have illustrated this for you, but I don't have enough appendages, okay? If there were 5 groups, it would look like this. This is 5 groups, repulsed at the most you can. See, the middle part is just trigonal planar. See, it's a trigonal planar, but I'm adding 2 more groups. Now make a total of 5 electronic groups. Okay, 5 electronic groups. And this is called Trigonal Bipyramidal. Why? Because there's a pyramid on this side, and then a pyramid on the other side. Okay, so it's Trigonal Bipyramidal is the name of this one. Okay, so Trigonal Bipyramidal, can you see that this bond angle is 120? And this bond angle is 90. So this one has 2 bond angles to note, 90 and 120. It's right here. This is with no lone pairs or no missing groups. If I remove one group, then you get this. Okay, remove one group. What is this? This is called seesaw because it's a little teeter-totter like you had in 1st grade. Okay? So that's why the molecular geometry name is seesaw when you move one group and change it to a lone pair. If you move 2 groups, it's now T-shaped. Notice now the bond angle is only 90. And if you remove 3 groups, notice it is now linear. It's now linear. So 3 lone pairs now, and now the bond angle is now 180. Let's go to the last one. Okay, this one is called octahedral. Anybody like growing up when they're in high school play like Dungeons and Dragons? No? Good, I'm glad you're not admitting that publicly. When you play Dungeons and Dragons, there's like more than 6-sided die. And kind of like this is called octahedral because of the faces. If you would make this into a die, it'd be 1, 2, 3, 4 faces here, and then 1, 2, 3, 4 faces there. So a total of 8 faces. That's why this is called octahedral. Okay? That's where it gets that name, octahedral. 6 groups for octahedral. Okay? If 0 lone pairs octahedral has 90-degree bond angles everywhere. 90-degree bond angles. Okay? And if you remove 1 group, let me do that. I remove 1 group. Now it becomes a pyramid, but the base is a square. So we call it a square pyramidal. So the electronic name is still the same, but with 1 group missing, it becomes square pyramidal. Here's how you draw it. 90-degree bond angle still. And if you remove a 2nd group, it becomes flat. It's just a square or an X. We call this square planar, as opposed to square or as opposed to trigonal planar. 2 lone pairs and bond angle 90. This whole page, you gotta know. It's not just this class. Every class has to know it. In OChem, you come back to it every single class. You need to be able to know these shapes. So in the textbook, it's 2 pages. However you want to look at it. This column is a later section, so don't worry about this at this moment. Okay, let me show you how this would work. How you would use these. What I'm going to do is flip backwards in my notes. And let's look at some examples just going backwards in your notes. Let's look at this one. And I'm going to make a little, on scratch here, I'm going to make a little note. What you need to do to be able to count shapes is to count groups around the center atom. What counts as a group? Because you need to know how many electron groups there are. A single bond is 1 group. A double bond is 1 group. A triple bond also counts as 1 group. A lone pair will count as 1 group. And then an odd electron or free radical will count as 1 group. So all 5 of those, or really any electronic species that goes together, or entity I guess I should say, would count as 1 group. So now if we look at this, xenon, again we're only going to do this for center atoms. Xenon has how many groups? 1, 2, 3, 4 single bonds and 2 lone pairs, a total of 6 groups. 6 groups. Because there's 6 groups, what? And you can kind of look at that chart on the reader if you want, or your textbook, whatever you have. How many, 6 groups is called what? What's the electronic geometry called? Octahedral. The molecular geometry, if 2 of the groups are lone pairs, is called what? Square planar. So the electronic geometry answer would be molecular. The molecular geometry, or the octahedral, molecular geometry name would be square planar. And you'd also want to be able to name the bond angle. What's the angle for a square? Just 90. These would be the kinds of questions we'd ask you. Okay? We'd also want you to draw it according to its shape, which I've actually done already. It's already at 90-degree bond angles. Let's try the one right before that. This one. Okay. I'll zoom out in case you're still writing. Okay. For the one on the top, for the center iodine, how many groups do you count? You should count 5 groups. 5 groups. So the electronic geometry name is Trigonal Bipyramidal. Trigonal Bipyramidal. The molecular geometry name, now you need to look at how many alone pairs are on the center atom. 1, 2, 3 pairs. So what do you think it's called? It'd be called linear. Again, if you look at the table on page 90 of the reader, Trigonal planar with 3 lone pairs is linear. It's linear. What would be the bond angle for something that's linear? Anything that's linear would be 180. Again, these are the types of things you need to be able to figure out for any Lewis structure you draw. Let's do another one. Let's do this one. On the previous set of notes here at the bottom, for the incomplete octet when we did that. For the boron. For the boron. How many groups? We counted 3, so what is it called? Electronic geometry is Trigonal Planar. Trigonal Planar. What is the molecular geometry name? Molecular geometry name, because there's no lone pairs on the center atom, it's the same. So when there's no lone pairs on the center atom, the molecular geometry name is identical to the electronic geometry name. For something that's trigonal planar or equilateral triangle, what would be the bond angle? (120). 360 divided by 3. 120. Is this drawn correctly? It's not. I should draw it so that it looks something more like this. Okay? Yeah. So I'm going to redraw this molecule to look something more like this. Okay? Let's do that. I'll just draw right here. That's it. Just draw it so that it looks how it should. By the way, before I do another example, make sure you check out your reader on different examples that I have. All those Lewis structures that you saw before and the Lewis-shaped polarity examples on the bottom page 93. Again, you can draw it, and before I do the answer, you can pause the video and see if you can get the right shape names and draw it correctly. I also have a video on there about how to draw each shape. You can take a look at the Vesper overview videos. It'll show you how to draw some of this stuff, especially at the beginning when you feel less comfortable. Let's try another one. Let's try any of these. We did this early in the class. If you look at any 3 of the resonance structures, how many groups are there? How many groups? Should say 2. Remember, a double bond counts as 1 group. A triple bond counts as 1 group. A single bond counts as 1 group. So you need to be able to count groups. There's 2 here, or 2 here. So that's the cool thing about resonance structures. You get the same answer for every resonance structure. Okay, so let's write this out. Electronic geometry name for 2 groups is called what? Linear. The molecular geometry name for 2 groups with no lone pairs on the center atom is the same. Linear. What's the bond angle for any linear? 180. 360 divided by 2. 180. And I've drawn it according to the correct shape. It's linear in my drawing, so the drawing is correct as it stands. I don't have to redraw it to look more linear. Okay, let's look on another page of our notes. Let's look at the carbonate ion. Each carbon has how many groups? Each carbon should have 3 groups, a double bond and 2 single bonds. Doesn't matter which picture you're looking at, 3 groups. So let me write that out, 3 groups. So the electronic geometry is called Trigonal Planar. The molecular geometry is, with no lone pair on the center atom, is the same. Trigonal planar also. Again, when there's no lone pairs on the center atom, then the electronic and molecular geometry names are the same. What's the bond angle for a trigonal planar? We just did this one. 120. 360 divided by 3. Have I drawn these correctly? I have not. I should redraw them. And on the final, we ask you to draw something, you better draw it to the right shape. Okay? I've drawn this T-shaped. It's not T-shaped. I'll just redraw one of them. Let me zoom in so it's easier to see. See, Lewis structures are cool. They're like little puzzles to solve. It'll look like this with 120-degree bond angles. Should look like kind of like a Y. Yeah. I say more. Oh, that's true. Yeah. If I've drawn this one like this here, but you know, even if I named this one Joe and this one Samantha, they would still be relatively in the same place no matter which way I draw it. So I could draw it like that too, as a Y, and that would be totally acceptable. Though for some reason when we do these, we put the 2 at the bottom. Just generally, if you see it in a textbook or on a paper, they would draw like this. I don't know why. Just common ways of doing things. Okay? I'll save some of the hard ones for the next lecture. I just wanted to do some of the more reasonable ones. Let's try some of these though. Try one, maybe 1 or 2 more. We'll leave the hard ones all till next lecture. Okay. Here, I'm assuming you can already draw the Lewis structure. Some of these we've done already, as you'll see. But these are just some examples where I did the Lewis structure for you, assuming you could have done that, and we'll just focus on the shapes. Okay? So, for this one, how many groups on that sulfur? 3 groups. So if you see 3 groups, what's the electronic geometry name? Trigonal Planar. Trigonal Planar. What's the molecular geometry name? You'll see there's 1 lone pair. Trigonal planar. The molecular geometry, there's 1 lone pair on the center atom. That means this is bent. For trigonal planar, what's the bond angle? Trigonal planar. 120. So I should draw this something like this. And And now there's a resonance structure to this one that I'm not drawing. But it pretty much looks like that. That bond angle will be 120, not 90. Again, it's an ideal bond angle, it's not the exact bond angle. We already did something like this. This one's hard. We already did this one, did that one. Let's try this one down here at the bottom. Yeah. No, we already did that one, didn't we? Did we do this one? Yeah, that one looks familiar. Well, we've done a lot of these. You guys are too smart. I guess that's enough examples. I want to say something about the next topic before you go. Again, we'll do more examples next time. Section page 92 in the reader. Back for a little bit. We've got a few more minutes, which is page 379 in the textbook. We go to this topic that I'd like to introduce right now so you have time to think about it, which is polarity. You've heard me use that word before. As far as polar covalent bonds, this is the same idea. We're going to use synonyms to this. A dipole is kind of be a synonym, and so will a dipole moment. Okay? Something that is polar is essentially polar covalent, meaning it has an unequal distribution of electrons. Okay, in a molecule. So the example you saw before was HBr, where Br is more electronegative. So you saw me write something like this: a partial negative by the more electronegative one, and a partial positive. So this has what we call a dipole. And we signify a dipole. Dipole is an uneven distribution of electrons with an arrow pointing at the most electronegative one and a hash mark at the end, at the other side of the arrow, the more positive side. Or if you drew something like CO2, this, what's more electronegative, oxygen or carbon? Oxygen. So compared to carbon, we'd have an arrow like this, but we'd also have an arrow like that pointing the other way. So that for this molecule as a whole, it has no, what we might say, net dipole. So while this one is polar over here, we would call this one non-polar. Even though it has bond dipoles, overall it doesn't have an overall dipole. Why is that interesting? This explains why things like water and oil don't mix. Water is polar, but oil is non-polar. And so if there's an oil spill in the Gulf of Mexico, that water is going to stay, that oil is going to stay on top of the water and not mix well, because one is polar and one is not polar.